And we're back again, back for more punishment. Did we commit last time? It seems we did not, so let's first do that. 05 halfway in example 1. Commit that. We're back again. So, third session of the day. Clearly I'm enjoying this. Hopefully it's enjoying to watch as well. Maybe you learn something. We've got this part working and we want to get this part working. That's the short of it. When I walked away for a bit of a break, there were a few things that came to mind that might be possible to simplify. I sort of was looking through the assembly and I noticed this. We worked out that this was the top of the stack. So then I was curious, like, can we just do that? Do we need to go fire a register? Operation not specified. Operation size not specified. This is where there's a keyword. Quad word, where a word is a byte, I believe. Data type in computing that represents a 64-bit unsigned integer or quad word. So the reason we had to add quad word is because we're saying, hey, compare the top of the stack to 0. And the CPU is all like, hey man, I really want to help you out, but I don't know how much of the stack. You know, the stack is just a block of memory. I don't know how much of the stack you want me to compare with this 0. And I'm using 64-bit registers, which does actually make me curious now because I just pushed 0. Does that automatically? And that's a 64-bit register. Anyway, I'm not entirely sure about this, but I think it's basically saying, hey, how much of the stack do you want me to compare to 0? And I'm saying, compare 64 bits, please. And it says equal. And if I go 5, it should say not equal. Okay. So that's a nice little simplification to the jump. Less is more. I like less. So we have just 2 lines here for a jump, compare, and then a thing, like so. So that simplifies that. I would also like to add some comments. So compare 64 bits. Let's say top of stack, back at 64 bits to 0. And here we want to say jump if above. And here we jump if 0. And we're also comparing the top of the stack to 0. So let's compile that. I'm just doing I just want to do a little bit of tidy up. The That's right. I was going to at the start of each video say what we're going to do. So first, there was just a couple of things that came to mind that I want to tidy up. The first was this jump where I identified maybe I could do it with less instructions, which we've done. And I think the second is that I want to have a comment. Basically, every line I want to have a comment. Which we mostly have already. Just with these print and halts, I just want to add a couple of comments, and that's it. That's all the cleanup I really wanted to do. Once we have done that cleanup, then I want to get this working. I want to be able to read and sub, and then we should be able to run the whole program. That's my goal. Doesn't sound like a lot for an hour, but the sub I think is going to be really easy. The read, I'm less sure about. Let's see. I'm not really sure how to do that. Maybe I should have done some investigation offline, but oh well. Them's the breaks. So our print. Oh, that's right. I wanted to do like arg0 to stand it out. Here is like arg1 is our buff pointer, and arg2 is our buff len. So actually, maybe we say it's a file descriptor standard out. So jump is all good, print is, well, we haven't done the syscall. Let's add comment to the syscall. That's how Fireship did it. He said call kernel, and then the halt also we're calling the kernel. I think that's it, actually. We've got comments everywhere. But I did want to say arg0 is the exit code. And maybe it looks a bit nicer to go file descriptor, and in this case it is standard out. Beautiful. Okay, that looks nice. So we go 06 tidied comments. Oh, I probably need to choose a file to commit. There we go. Now, read, the dreaded read. I'm really quite happy with how far I've got already, but the dreaded read. Okay, let's go x86 NASM Linux read from console. That's like an argument to the program. Input and output. user input and output. This we went to this website before, and I think I remember it was quite helpful. Need to remember that. Convert number to string. Interesting. Okay, reading numbers. Reading numbers. This is what we want. Read from console. He's using the E registers. x86E versus R registers. 64-bit registers using the R prefix. 32-bit registers using the E prefix. Okay, that's what I thought. So I think we can just, what is this int command? I think we can just, oh, there's one other thing that I thought would be nicer. We can do strings.concatenate. Like that. I think that's a bit nicer than having this multi-line madness. So here we want to have the string and then the rest, and then a syscall. So that's tidied up our print. Our jump, we can do something similar. Strings.concatenate. That token, and then that. And this is the same, but it is JA, jump if above. Just comment out that, run it and see. Yeah, I think it looks good. I do notice there's a space at the end of this one. So that is the jump. Yeah, 0. Okay, that looks good. And I think we also did the same thing down here. Yeah. So strings dot concatenate. Put this in here. Index string. And then that. Then the string constant. Then just another double quote comma. Length string, and then a new line. So that's all of that. I guess we could just go boom, 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 take you and put you here. Run that. I think it looks pretty good. Yeah, seems happy. Okay, that was a little more cleanup. We could just Get rid of that and then just amend that commit because that's part of the cleanup. Okay, and then we'll get back into here. So I guess we do want the rest of that actually because we want to put our read first. Now we want to move something into RAX. Are we doing a syscall? We're not doing a syscall. Let's see if he explains what's going on here. Place the file descriptor for standard in 0 in the EBX register. Put the memory address of a buffer to store the input in the ECX register. So it's in buffer, which is this here, just some amount of space that we've allocated. Store the buffer size in the EDX register. So yeah, we said it was 16. Set the EAX register to 3, which is a read syscall. Yeah. Yeah, he's put that in number 4, but he's put it at the top, which is where I would have also put it. And then what the fuck? Call the int OX80 instruction? Ah, you do that instead of syscall? This is a bit strange. Okay. 6, convert the received string to an integer. Convert string to number. Okay. And what's this convert? And store it in the EAX register. Jump to convert. If we find a new line character, we're done. So all of this is converting the string to a number. Yeah, I thought this was really going to be something. All right, let's create our BSS section. Let's just put it at the top. We couldn't put our data section at the top because we need to move through all the instructions to find out what we're putting in it. But here we're just going to hard code what's in here. So section BSS, and here it's 16, is that 16 bits, 16 bytes? It just mentions that it's the size. 42, if we put in that into a buffer, that's 2 bytes, hence 16. So let's see, we'll do it with the 16 like he did. I have a feeling it's only going to handle 2-digit numbers. Anything above 2-digit, I don't think it's going to work. So move rax 3, that is syscall read. Am I right? Syscall close. Open. Read. x86 assembly NASM. says set the EAX register to 3 for a read syscall. But over here, the read syscall is 0. I'm gonna go with that documentation and say that it should be a 0. RBX is also 0, which I think is the standard in. No, that should be RDI. Yeah. Maybe it's because he's doing 32-bit that all these are named differently. But he's also got a different number for the syscall. It's like, I don't know. I'm a bit confused by this. And then he's saying buffer. He's saying LEA. x86 NASM LEA. What's the purpose of the LEA instruction? That's what I want to know. For me, it just seems like a funky move. What's its purpose and when should I use it? Shift and add instruction. It was probably load effective address is often used as a trick to do certain computations, but that's not its primary purpose. Support high-level languages like Pascal and C, where arrays, especially arrays of ints or small structs, are common. I can't be bothered reading all of this, but load effective address into ECX. So I guess ECX is supposed to be the buffer. So we're talking RSI. So arg1 is buff star. With the right, I guess it's actually like, no, let's not get too fancy. Well, sorry, which register was it? RSI. RSI, we want to do, I think these brackets is kind of like address of, right? So we're saying the address of the buffer. We're loading the effective address into RSI. I just did a move, but let's see. I'm taking this example, and so far I have not done any instructions the way he did them, which makes me very skeptical that it's going to work. The last line is just the syscall. Then we have move EDX16. What was that about? That's the size. That's right, the size. So that's the RDX. RDX. And I'm just going to hardcode 16. So, and that is the arg2 buff len. Like that. So I think that's a read. Start with the read. If I run it, it hangs. Interesting. Press enter twice. Because there's two reads at the top. It's calling read twice. read. Okay. So I'm just going to do this. Just start a new section, because then what we want to do, I'm a little bit worried about this. Because we're writing like a whole bunch of assembly, and how do we confirm if part of it is working? You know, well, if we're putting it into a buffer, we know how to print. Here's our printing code. So can we test the part we have so far? By saying, well, we already have these in RSI and RDX. So all we need to do is change RX and RDI and call the kernel, and it should echo, basically. This should echo. So well, I didn't see it echo. Maybe we do need to load effective address. Yes. Okay. We did need to load effective address. So it is echoing, and I was thinking that it only holds 2 characters. So if I go GGG, no. But is that like a buffer overflow? Okay. I don't think I'll figure this out, but I'm really glad that we've at least verified that the read has worked. Now we have to do this convert string to number. So let's do it. This is interesting. Because we have 2 reads. If I just output this twice, where's it going to jump to? There's going to be 2 convert labels. I think I need to have just something at the end Yeah. I think I need to put this at the end. But it needs to know where to jump to. How do function calls work like that? I mean, you can't. Is that what a return is? But this is recursive. Yeah, I don't know. So I think the easiest way to do this is if I just have something that outputs this code. and it has a done, it has a unique label here for each instantiation of this, and then also has a unique done, which is basically just after this. Yeah. So then I can just insert it anywhere and it will perform this and then go after. Yeah, I think that's the easiest way to do it. So I'll say, what is it, like string to int? We'll call it buffer string to int, because I'm hard coding that it comes from the buffer, the string. String to int proc, like so. Let's take this, put it in here. And can we just have like a global variable here, which is index. So then every time we run it, we just append the index to these labels. Okay. I think that should be not too hard. So commands are indented by 4. But I do need to pass in out, which is a string buffer builder. Strings dot. That's not strings. That's strings. Let's say I pointed to a builder. Buffer string to int. So we want to XOR RAX. RAX and RAX. RAX is where what do we have in RAX? Don't need this here anymore. XOR is exclusive OR, so it's in one or the other, but not both. One or the other, but not both. So I guess that's just a way of clearing out. I mean, can't you just move 0 into RAX? I don't know. That seems a bit strange to me. Okay. Then we're loading the effective address into RSI. Did we? I don't think we. We did. But you know the effective address is already in RSI. He's putting it in a different register. Then we have the label. So we're going to have to do strings.concatenate for this one. Like so. Oops, just comma. With that index. And at the end of the function, we're going to have to just go plus equals 1. So next time we call it, we get a new index. Oh, I need to convert that index to a string. I feel like I'm not doing a good job of that. So we can probably just move that to there, because we're just going to use index string. So we'll say underscore that. Let's call it the loop. Don't think we need a comma on a comment on a label. Okay. On to the next command, which is this, whatever the fuck that is. Can I do RSI and just comment that out? Like, we've already got it in RSI. And say, so move ZX. Move with 0 extend. Copies the contents of the source operand register and memory location to the destination register, and 0 extends the value. The size of the converted value depends on the operand size attribute. So we're saying move the first byte of the buffer into RDX, basically. Oh, and then we increment ESI to move along the buffer. Okay. Move first byte of RSI to RDX. Compare DL. Check for a new line. And if so, we want to do like need a string concatenate, but I want to jump equal. Okay, jump equal to the end label. Jump to end. So at the very end, we need to have, wait a minute, that should be like that, but at the very end, we need to have that label. Like So if jump of equal to the end. Now they do integer multiplication, subtraction, addition. So I don't really understand those commands, but I think they'll be fine. If we just replace it with racks. So how did something get into, so this started off as 0, and now you're saying, I don't know why we don't just move 0 into Rx. I think we're saying multiply Rx by 10. Subtract the character 0 from here, which should give us the integer. Interesting. And then add that integer to Rax. That actually makes total sense. Multiply int by 10. I do think we can just move 0 into Rax here. I think that's a bit clearer. I don't know if XOR is supposed to be faster or something. This is, when it comes to optimization, I have no idea. So EDX, we used RDX. We subtract the character 0. Subtract 0 to get int value of char. And then we add int value of char to final int. To result. So maybe multiply result by 10. Then we increment ESI, which I've called RSI. Let's see if that works. And RSI, which is like move to next char. We keep moving to the next char until we get to the new line. This is actually really interesting. This is the most in-depth assembly code so far, for sure. And I feel like I'm understanding it, but I'm not sure if I've really explained it very well. Let's wait until we get it printing out, and then I'll run through. And then we jump to convert. So there's only one more. Instruction. So this is just a plain old jump. It's not jump like up further. We have another jump, right? Jump of equal. This is just jump. So we're going to jump to, we're going to need to do this. I think we're going to need to do a string concat. We don't need the colon. Jump. So we're going to jump to the top of the loop again. Top of loop. I find this super interesting, actually. Let's leave that comment there for now. Let's print that out. So we get to the read. Shouldn't it be in the read? Oh, no, because we've made this a function. Hey, kitty cat. So what we need to do is add this here. That should take the buffer string to int. Jump to end. Okay, we obviously have a misplaced new line in here. Where is it? So when we jump if equal, and we put a new line before the semicolon. Yeah. So it should be jump to end, then semicolon. That's better. Okay, so here it is. So here we proved that we got the input from the user into the buffer, right? And the effective address of the buffer is in RSI. That's where we're at. Now, this XOR, I find a bit strange, but we'll leave it here for now. Oh, maybe I should confirm. Yeah, it looks like we still have more issues. It's this, oh, that's not needed. This jump here should be indented a bit more, and we have that same issue. Yeah, I think that's right. Okay, so that's where we're at. We have the buffer in RSI, basically. We XOR RX and REX. XOR, exclusive OR, means just keep something that is in one of these but not the other. Because these are both the same thing, that's not going to keep anything. You know, both of them, like say they were both, just to keep it simple, 4 bits. They were 0, 1, 0, 0. So both of them have a 1 in the second one. Because it's exclusive OR, it can't be in both. So it won't keep that. So effectively, I think this is just clearing it out to a 0, which makes sense because this is kind of like the running sum of our integer. We need to start at 0. So I think I want to change that to be just more explicit. Move 0 into RAX. Well, let's keep that as it is for now. Now we start our loop. And we move the first byte of the buffer into RDX. So the first character of the buffer goes into RDX. Okay? This part here we need to work out, because I don't know what this DL business is. But I think basically what we're saying is, did we find the new line character yet? If we found the new line character, this is the end of the string, the end of the input. You know, because the user types some characters and then they press enter. So the last thing they do is a new line. So this means that it's the end of the user input. So jump if equal to, oh, interesting, he's got jump if equal, but he doesn't have a 0 after, because I think in my jumps, no, you don't need to do that. That's true. Okay. So then if it did find a new line, we jump to the end down here. And we just move to the rest of the program. We're done. And we have a 0 in racks, basically. So actually what we will need to do after this, let's do it now. Is we will need to, at the end, oh, no, not at the end of this. After we do this, maybe we do another new line, and then we want to do push racks. Push result to stack, something like that. We want to do that right at the end. Push result to stack. So if we had jumped out straight away, we went to the end, Rax is still 0, we push 0. It means the user didn't input anything. And this code assumes that they've only inputted numbers, I think. I don't think it does error handling if there's no numbers. We can try that, but I think it's not handled. Anyway, so let's assume we didn't find a new line. We multiply the current result that we have by 10. In this case, we hit our current result is 0, so that doesn't do anything. So in the next loop, that will become clear why we need that. Then we subtract the character 0 from the current character. Because if you think of like ASCII characters, the way they are laid out, actually, let's go ASCII table, and we find the numbers. Here are the numbers. So 0 is 48, 1 is 49, and all the way up to 9, which is 57. So if the current character we're looking at is, say, a 5, and we subtract the character, which means it's a 53. That's the number we have in the register is 53, because that's the number that correlates to the character 5. Now we subtract the character 0, which has a value of 48. 53 minus 48 is 5. So we've converted the character 5 to the integer 5. I think that's pretty cool. So now in RDX, we have the character, whoa. We have 2 subtractions in a row. I feel like that is wrong. Sub add increment. Yeah. Yeah. Also, it's add RAX, RDX, RAX, RDX. I think the add in value of chart result. So the comment was right, but the command was totally wrong. Okay, so say that it was a character 5, like we said. So now our dx so I think what this does is it subtracts this from RDX. Yeah. And then I think it puts the result also in RDX. So now RDX, instead of containing, what was it, 53 for the character 5, it contains the number 5. Now we add 5 to RAX, which is our kind of our running result, or our current result. So now the result is 5, which is correct. If the user only input 5, we now have the number 5 in RAX. Perfect. But what if they added more characters? Let's say they typed in 57. So we increment RSI, which effectively moves us, because remember RSI is where we have our buffer, right? So incrementing RSI effectively moves to the next character in the buffer. So now RSI is pointing to the second character, which is the 7 in our example, if the user typed 57. And then we jump back to the top of the loop. So we're up here again. Now we do this move ZX, which effectively puts the next character, the 7, into RDX, which is, I guess, 55 in ASCII terms. That's the number 55. We need to review this. Yeah, I need to review this because I'm not sure if this is right, but this should be checking whether we just read. Should be checking whether we just read a new line. And if we did, again, we go to the end, but we didn't yet. We read a 7. So now we multiply what we had in RAX by 10. We had 5 in RAX because the first character was a 5. So we multiply it by 10. Now it's 50. Remember, we've typed in 57. So we've got 50. Now we subtract the 0 character from RDX. RDX has the value of our 7 character in it, which means that now we've effectively, this converts the 7 character to the 7 integer. Now we add RDX to RAX. So RAX, remember, had 50 in it. This has just got 7 in it. So now, after this operation, RAX has 57. So for both the sub and the add, it's like with the add, it adds these together and puts the result also into RAX. So now RAX has 57. Now we increment to the next character, move back to the top of the loop, grab our character from the buffer, check if it's a new line. It is a new line in this case because there was just 57 enter. So then we go to the end. And now we take our value and we push it onto the stack because that's how our program works. Stack based, so the result we wanted on the stack, done. That's really cool. So this part here is what I'm not sure about. We're nearly at an hour. I'd be really stoked if we could get this working. x86 NASM comp DL. Maybe we can do comp DL. He doesn't explain it in here really, does he? I mean, he explains in detail this part, but he does not explain the conversion part. Maybe we can go to the reference for comp. BL. He did DL. What is DL? This is like the last piece of the puzzle, I feel like, but I don't know. He just comp DL, but he moves into DL also. Then he comps DL. I feel like we moved into RDX. We should compare RDX, right? Doesn't that make sense? We compare RDX to this, which I guess is the new line. OA, which I think is just 10. Let's go back to our 10 line feed. Yeah. Hex A. Yeah. So I feel like we just compare RDX because that's where we put it. But we need to do that actually in here. I don't know where that DL came from or what it means. Let's see. So we're getting a number, we're pushing it. Let's take away this push 0 at the start. So we read a number, converting it to an integer and pushing it. We do the same thing again and push it. and then we're doing where jump if equal to 0. Okay. Oh my God. I think it worked. We're at an hour. Do we want to do the sub? Do we want to do the sub? Because if we do the sub, we've basically done it, right? And I think the sub is really easy. Sub. So actually, we basically want to pop to RAX, then pop to RBX. So this is the when we do our subtract, if we go to our interpreter, the first one we pop is the right-hand side. So let's call that right-hand side. Let's call this left-hand side. And then let's go sub RBX REX. And then push RBX. Subtract. Push back to stack. So it's like pop right hand side from stack and pop left hand side from stack. Then we do our subtract and then we push it back. So if we run this and we say 4, 5, that's not equal. But if we say 4, 4, that is equal. Wow! We got the first program running. It's quite, I mean, it's 83 lines. Now I feel like really this should be a function call. And it's like I to A to I. They might be like built-in things that we can call instead of having this, although this was really interesting to write. But I'm so surprised, because from what we were given, I modified it quite a lot to work with these R registers, and I just kind of did what I thought made sense, and it worked. And it was really fun too, because when I first saw this, I was like, I don't know what the hell is going on here, but as reading it through, it makes sense. It makes sense. So we have 82 lines of assembly, including our strings and everything. We can read, we can write, we can do maths, we can jump, we can exit. Yeah, we have our jump, print, hold. It's very nice. I have to say, it's very nice. Okay, we did go a little over an hour, but I think the extra 5 minutes was worth it just to like get it all working. Wow. Ciao.